Hello everyone. In this video we're going to look at an example that uses African antelope humerus lengths and diameters to look at a situation that may allow us to use power regression or a power model. So what you'll see on the screen here is a list of about 11 humerus diameters and 11 humerus lengths in millimeters. So what you're going to want to do is you're going to want to pause the video so that you can enter this information into your Inspire. Go ahead and put diameter in list A and length into list B. So you'll see that's what I've done here in my calculator. I have diameter here on the left and I have length here on the right. So like we've said in the past, every regression problem we're going to want to start by graphing the data. So I'm going to create a new data and stats page and I'm going to put diameter and then I'm going to put length. So we look at the data, and the first thing that I notice is it doesn't immediately appear to be awfully curved, but if we look at a residual plot, we may see otherwise. So in order to get the calculator to calculate the residuals for you, you're going to need to fit a straight line model to this data, to the data. And now you might be able to see the curve just a little bit easier. So we'll create a new graph page, new data and stats page. We'll put diameter on X, and on Y we'll put stat.resid. And now we see in this residual plot that we do have this curved residual plot. At this point you would want to sketch some rough graphs onto your paper. You would include the scatter plot, which we would describe as a strong, positive, slightly curved relationship between length and diameter of the antelope's humerus. And we'd want to include the residual plot as well. And we would state that the residual plot shows a clear curve, suggesting that a linear model is not appropriate for the antelope humerus data. So now we'll kind of move on to what transformations we might end up trying. And we'll actually begin with the same transformation we began with in the last video, and that is to examine the possibility that an exponential relationship might be appropriate. When we return to our calculator screen, you're going to want to go back to your List and Spreadsheet tab. Back on your List and Spreadsheet page, we're going to begin by finding the natural log of length. So we'll give that cell a title. And in the formula bar, we'll go ahead and type in natural log of column B. And it will give us all of our transformed values. So now we're going to want to create a new scatter plot. Using, again, diameter as our x value, and then this time we're going to use the natural log of length as our response variable. And you'll notice that in this particular case, it may have actually made the data worse. I can clearly see that this is curved. I don't think I have to take a lot of effort to examine a residual plot to see that this is curved. So let's go ahead and return to our original data. And now this time let's also take the natural log of diameter. And then we'll create another scatter plot. So this time natural log of diameter and natural log of length. And now we see a relationship that that may be fairly linear. So we'll go ahead and fit a straight line model to this. So there's our linear model. And then let's also look at a scatter plot. I'm sorry, a residual plot. So we'll put natural log of diameter as our x variable this time. And then we'll use stat.resid. What you'll notice when we look at this residual plot is you may see this and say, oh my goodness, there's an incredibly large residual there. But what's really interesting is if you look over here on the left-hand side, you'll notice that these residual values are incredibly small. This large residual, if you could call it that, has a value of negative 0.0025 approximately. So when we look at this residual plot, it almost actually resembles a residual plot that you would see if it was a perfect linear relationship. So while this one may look a little bizarre at first glance, this y-axis tells us that there's nothing strange going on here, that this model may actually be a very good fit. So here is our scatter plot, our final scatter plot, and now it'll be time to actually look at our model. So we'll go ahead and write our equation now. So it's a power model, so we're going to have the natural log of length as our y variable, and then our intercept is 3.18 approximately. Our slope is 0.66 approximately, and then our x variable is going to be the natural log of diameter. So there is our model. Now, if we wanted to make a prediction, we're going to end up having to work with these logs again just a little bit, which isn't a huge problem. So perhaps maybe we're going to be interested in a prediction that's not on our table. So if we look back at our table, maybe we have an antelope with a humerus diameter of about 55 millimeters. So let's see if we can calculate a prediction for that. So we're going to begin by substituting 55 in here. So we're going to have the natural log of length equals 3.18 plus 0.66 times the natural log of 55. So this is a little bit different from some of the ones we've been looking at before, because now I'm going to actually have to take the natural log of 55 before I then multiply it by its slope. So when I use my calculator to find that result, I find that the natural log of length equals about 5.82. So our final step is going to be to find out what length should be. So in order to do that, I need to take e raised to the natural log of length, and I need e raised to the 5.82. And based on log rules, e raised to the natural log of x becomes x, or in this case, predicted length. So our results, when we plug e raised to the 5.82 into our calculator, we get about 336, 337 millimeters for the length of the antelope's humerus. And if we look back at our original data, we would see that that seems to fit pretty nicely. So we have 55 would be in between these two observations here, and that would put our predicted value there. So 336 fits really well. So that's how we would use logarithms to perform a power transformation.